Hello, everybody. Today, we're going to talk about something very exciting that we are doing with the Indian Railways. There is this boring topic called underwater bridge pillar survey. Using my energy and our technology, we're going to make it interesting for everybody. For that, let's go select a rail bridge. So, this rather simple rail bridge located in Tea, district Bardhaman in West Bengal, is a major rail bridge for the Eastern Railways. If you look closer, there are two bridges. One bridge is constructed directly in the river. The second bridge is constructed single span across the river without any pillars in the water. So when I started looking at underwater surveys and what is the interaction of flowing water and bridge pillars, it brought me to something called scour. What is scour? Scour is a phenomena that happens in flowing rivers when a bridge pillar or an obstruction is constructed in the water. This causes a pressure difference between the upstream and downstream side. This pressure difference makes the water from the upstream side get sucked down to the bottom, and then it exits around the pillar in the form of vortices or whirlpools that erode away the soil and the dirt and the rocks that is keeping this bridge pillar intact. Sometimes, if the water is fast enough, it can erode the bridge pillar itself, causing damage to the bridge. This bridge is constructed on the Babla River. The Babla River is a tributary of the Ganges and is a fast flowing river. Further, when I was crossing this bridge, I noticed there was a speed restriction in place, and that got me interested in looking at what is underneath the river pillars and underneath the water. So to look underneath, we're going to use our sonars, which you can find in banerjee.com/sonars. And the sonars give us a clear image of objects underwater. So how does this work? Sonars are acoustical devices which work by sending a sound wave in the water. For this, we have a transmission set that generates a multi-frequency sound wave. This multi-frequency sound wave propagates through the water column and gets obstructed by fishes or submarines or boats or bridge pillars or scour or rocks, and then gets reflected back. This reflected wave then gets captured by a second device set, and this received wave is further processed with a few layers of signal processing, and then we can see what is underneath in the depths. So, for this mission, I'm planning to use a variety of robots to capture all the data. We'll be using aerial robots, our surface vessel, and also
our underwater robot. Here I have with me two eyes of the jewel of knowledge, the sonar crystal, the eye that sees the unseen depths. And I'm planning to use 21 of these to look what underneath the river. These would be fitted on our water drones. Additionally, I will have this high resolution, low light HD camera, and I'll be using 5 of these on all our robots. So, with our 21 eyes, 5 HD cameras, multiple drones and robots, we will get a very clear picture of what is underneath the Babla River. And by the time we are done, we will have over 200 million data points, which will paint the riverbed and the bridge structure clearly. So let's go to Taya and take a look. So with our 21 eyes, 5 HD cameras, and multiple robots, I'll see you all in Taya.
All right. So, what do you get when you mix fast flowing rivers with structural girders holding up railway bridges? Scour! And that indeed is the need of the hour because Banerjee is here all the way in beautiful Tia. And we're working with the Indian Railways to figure out the power of scour.
Let's go.
Welcome back to Banerjee HQ. I'm Rishabh Banerjee, the Director of Engineering here, and together we're going to talk about the technical details of this operation. Um, During Octania, we obviously used multiple drones, leveraging our multi-domain sensor fusion technology, allowing us to get a holistic picture of what's going on under the water, near the surface, as well as above the water. Um, Using our surface vessel and working both upstream around the target pillars as well as downstream of the river, we were able to assess not only the bed map but also the flow velocities and the flow patterns associated with the river. With this understanding of the bottom topography as well as how the river flow is occurring at the surface of the river, as well as looking at an aerial view of local construction, embankment, geography, as well as local activity, we're able to come up with a holistic view of what is going on at the site and how the situation may progress in the future. This is going to give key insight to the railways as they try to maintain a huge amount of assets across the country. They're going to need more data, they're going to need more insightful data, and that's exactly what we're trying to do here at Banerjee. Give these data tools to the engineers who really need them to keep the most critical infrastructure running in the country. So, enough talk, let's dive into the data. Here we have Bridge 217 of the Eastern Railways with the Katwa and the Azimganj ends labeled, as well as the downstream and upstream sections of the river labeled. What we can see from this picture is that the construction of the bridge itself has created a narrowing. When you compare the width of the river upstream and downstream to the width of the river at the bridgehead. We defined this area as our area of survey, and we began our work with the underwater remotely operated vehicle. Here is the camera feed of the ROV, which you can see is clearly degraded because of the turbulent nature of the river as well as the turbid water quality. So we decided to pull the ROV from the river at this time and conduct our operations with the aerial drones as well as our fleet of unmanned surface vessels. Here you can see the aerial drone doing a flyby of the surface vessel as well as our team on the boat and the shoreline there. You can also see the construction of the bridge here, which we are investigating, as well as the bridge pillars. And now you can see the feed of the upstream section of the river, where we are looking for any disturbances in the flow. We are not able to observe any irregular geography or construction or on the shoreline, nor are there any obstructions or debris in the body of the river. The flow seems to be gentle and consistent. Now, with all our sensors, we are able to generate a three-dimensional point cloud of the riverbed and its surrounding terrain, which when aligned with our key object of interest, the bridge pillars, we can then interpolate and generate a three-dimensional bed map of the riverbed and its surrounding terrain, giving us a clear understanding of how the river flows as well as how that might change into the future. Aligning this bed map now with the geography, we can see the Katwa and Azimganj end as well as the downstream and upstream sections of the river marked here. What is firstly evident is the clear depression zone that's generated here at a 7 to 9 meters depth, which should be contrasted with the average upstream depth of about 5 meters. There's also these characteristic rocky deposits at a depth of about 2 to 4 meters around pillar number 2 and 3, as well as the Katwa end of pillar number 1. Looking at the area closely with the side scan sonar, we are able to locate the bridge pillars as well as their characteristic acoustic shadows, as well as the rocky deposits around the bridge pillars. Looking at the flow morphology, we see the flow approaches the bridge at an acute angle, hits the shore or the Katwa shore, and rushes past the bridge pillars into the depression zone. The flow velocities are between zero point 0.5 and 0.7 meters in upstream and between 1 and 1.5 meters near the bridge pillars, decelerating to 0.6 meters in the depression zone, generating whirlpools right after bridge pillars 2 and 3, which are going to be the major cause of natural scour in that area. Here you can see aerial drone footage of the front of the downstream section of bridge pillar 2, and you can see those whirlpools being generated. We took a closer look at all of the pillars with our one-dimensional sonar, and here we are able to detect the presence of some boulders or rock-like structures right next to pillar number 1. You can see the rock-like structure giving us a solid red return here. But there is a different and much more interesting story when we look at pillar number 2, especially the southwestern or downstream Katwa end of pillar number 2, where the return seems to show a solid bar between 2 and 2.5 meters, but then below that, what seems to be a void. When we remeasured this area several times, the same pattern reemerged, leading us to believe that there could be a local loss of material or a local porosity in the area of bridge pillar 2. And this could be a potential case of local scour. Now, looking at the bed map a little more closely and understanding how the flow of the river is developing, we can see that the upstream section of the river is quite uniform and rather with a gentle gradient. But we can see that the rocky deposits are forming an entrenchment for the and constricting the flow towards the depression zone. Because of the deposits, we believe that the flow is accelerating due to the constriction in the height of the river, and then on decelerating in the depression zone, creating whirlpools and the scour field, which we are seeing pictured here. You can also clearly see the effect of this from the difference in the height of the downstream and upstream sections.